I feel like I
There's
ask
no
stupid
such thing as a
questions.
stupid question
I ask
until you work
stupid
in customer
questions,
service.
and you ask long questions. I think that's our problem. Like my
No, I
questions.
feel like my questions are just stupid.
No, yours are just
mine
long.
are just long and
Yours
stupid.
are just long questions. I think that's your problem.
My dad's
Mine is
favorite.
just bad ones.
My dad's favorite saying is, "There are no stupid questions, just stupid people." I don't know if I agree with that or not.
Oh, I 100% do.
There are stupid people. There are stupid questions. I like to say there is no such thing as a stupid question, except I worked in customer service for 7 years. So
Yeah. That's basically what I do, and like it just
that
makes
was
you
my
hate
career for 7 years, was
Wait, what-
answering stupid questions.
What did you do?
I was a server for 7 years. I served tables.
Name the dumbest question someone's asked you.
people. Do peanuts contain peanut oil? Have a sheet of paper.
I don't even know. I try to tend to forget those things, but I had a lot of crazy ones though. I mean, it just comes with the job. There was one time, this was near the end, there was one time that I had a two-top, so there was an older guy and an older woman. The woman was on my left and the guy was on my right. And I came up to the table and I was like, my typical intro, like, hello, it's my name, I'm here to serve you, like, what can I get for you, whatever. My typical intro stuff. And then she goes, we'll have 2 chocolate malts. And I was like, I'm really sorry, we don't actually have malts. I have chocolate shakes, we just don't have the malt powder to make a malt, so is a chocolate shake okay? And she was like, no. You have malts, we want chocolate malt. And I was like, sorry, we really don't have malts because I don't have the malt powder to make a malt, but I can do a chocolate shake if that's okay. She's like, yes, you do. And I was like, no, I'm sorry, I really don't. I don't know. And she's like, yes, you do. And I'm like, I don't know what you want me to do. I was like,
You want to rip your flow?
like, I can't do anything. I really don't. Like, and she's like, wait. So I can't remember then. She asked something, and I was like, do you want me to like grab my manager to like tell you that we don't have malt powder? Because like the manager, we don't have malt powder. I don't know what to tell you. And then she's like, oh, fine, whatever. And then she like sat there for a few seconds, and to the point where I was like, should I leave? Like, it was just silence, and I was like, I don't really know what to do. This is really awkward. And then she goes, we'll have a Diet Coke. You don't even want the chocolate shake? Come on. You made me do all of that, and you're not even going to take the shake. Ridiculous. So that was one of like near the end of my years. I was like, are you serious right now?
She does not believe you.
Chocolate
I'm
malt.
like, I don't know what to tell you. Like, that's just what it is.
We'll do
All right.
chocolate malt. If you don't have that, I'll take asparagus.
Pretty much. We'll both have a Diet Coke. I was like,
Okay.
okay, we could have avoided that whole 3-minute interaction. I'll be right back. All right.
At that point, you should have just gone back and gotten a chocolate shake. She probably wouldn't have known the difference.
No, that's the thing. So that's what I figured probably happened is either, because she said, after she said, yes, you do, twice, she said, we were here 2 weeks ago, or last week, and we got a chocolate malt here. And I was like, well, either you were at another Perkins because we don't have it, or you were served a chocolate shake here and thought that it was malt. Both of those were entirely likely. So,
Where she
I don't
has
know.
dementia.
she wasn't really that old.
Early onset?
Probably. Maybe.
All right. Anyways, that was my fun story for the day. Calculus. We're starting. Okay, so we've been doing a lot with integrals, and we've been calculating definite integrals, finding the actual value under a curve bound by the x-axis, and then we've also been doing indefinite integrals, which is just generally finding antiderivative formulas. For the rest of calculus, we are doing one last module, and it is the applications of integration. And so this is one of our first applications, is finding the area between two curves. Now, that doesn't really sound like a great application, except when you consider the fact that basically everything in life is actually the area between two curves. Like, even you look at this table, it has curved corners. If you wanted to find the area of this table, you would have to actually be able to calculate underneath of a curve. You want to find the area of the surface of the chair that you're sitting on. Like, you could go and name anything if you want to find the area of something. It's probably actually a curved surface. It's probably not like a rectangle. I mean, this is like the only rectangles you'll normally see is like your walls and then like a whiteboard. You know, like lots of things are just curved. And so this is actually a super applicable thing to be able to directly find area between two curves. Okay, how do we do that? How do I calculate this area? Consider the graph here. What do you think?
Oh, what I said last time was like, for some reason I kept thinking of this concept where it's like, imagine like where red and blue meet, you pull like a straight line down.
Okay, are you saying like right here at the
Yeah, so like
intersections?
do a straight line from there down to the x-axis.
Okay.
And then you have it on both sides. And basically you find the area from red all the way down to the x-axis. Yep, and then, oh yeah, that's what I was saying.
Like
yeah,
that?
Yeah. And then you just subtract area under blue from area under red. Because it's just two integrals. What am I thinking that from? Do you know what I'm getting that from? I feel like it's algebra 2.
Probably you've done something in algebra like this where you've had the area of a rectangle and then a rectangle inside, and then this is shaded.
Oh man.
And we want to know, hey, what's the area of the shaded part?
Oh, okay.
So you would find the area of the outside and then subtract the area of the inside that's not shaded. You've probably done something like that. Okay, yeah, that makes sense to me. Find this total area under red, and then find the area under the blue, and then subtract that away. That's the missing part right there. You see that? Okay, great. That's pretty much the whole idea. Like you are pretty much already mastered it. So great.
Couldn't you just, why wouldn't you be able to take the y, the topmost y point and the lowest y point, and then just draw like a straight line through the middle of that, and then just take the upper and lower bound. That way you have like a new x-axis. Would that not work?
Between these points? No,
On the y-axis. On the y-axis. So if you have your y-axis there, the
Okay.
bottommost blue point on the y-axis, and then the uppermost red point on the y-axis, on the line, and then you take the halfway
right
point.
here,
Yeah, like right there, and then right there, and then you take.
here,
No, on the white line.
okay,
Yeah.
like there.
Yeah, like right up there,
Okay.
or it'd be like on the red.
Oh.
Yeah. And then you take the halfway mark between those two, and then that might serve as like your new x-axis, and so then you just do a Riemann sum on the upper bound and then the lower bound.
Oh, like, okay, so you want to add a line right here.
Yeah.
And then just find this area and find this area.
Mm-hmm. Would that not work? Because I feel like that.
Okay, yeah, that I think that would totally work in this situation.
Oh, so you're like making your own x-axis.
Yeah,
Basically.
sure. Yes,
I don't know.
that can be done,
Mhm.
and so that's a great idea. It will work in this situation. I can't promise it'll work in every situation. And also, the challenge is, how do you calculate that with a different x-axis anyway?
That's not right.
So that could get hard as well. But it can be done. It's actually a topic that we'll try, I think, to explore near the end of our last module here, is calculating things with axes other than the x-axis and y-axis. Okay. Okay, so that's the basic idea. So let's actually do one. Let's calculate the actual area. So here's a couple of functions. Calculate the area bounded by the curves y equals x to the fourth and y equals 1. The basic idea is we're going to find we need to find the area of one of them and then subtract the area of the other. So a couple of things that we should know about that. We need to find the area of the top function and subtract the area of the bottom function, right? Because if we tried to find the area of this and subtract this, that wouldn't work, right? So that's one thing that we'll need to think about is which one of these is the top function that we would need to start with first. Then we would need to find the integral from wherever to wherever, find the integral of that one, and then find the integral of that one, and then subtract the values.
Yeah.
Okay? Let's give it a go. Let's start by graphing this, because that'll really help us see which one's on top, visualize the actual area we're trying to calculate. Let's do that. Let's actually draw this on an axis, on a coordinate plane. Okay. What does y equals x to the fourth look like?
It's going to be an upward parabola.
Okay. Let's do some points. Let's try to be accurate on this one.
You're gonna have 1, 1.
1, 1. Okay, yes, 1, 1.
You can have 0.
What?
You're going to have a 0. 1, 0.
0, 0?
Yeah.
Okay.
You have a point at
Negative 1, positive 1.
Okay, negative 1, positive 1.
And then the next one is 2. 2 times 4, 4 times 2 is 8, 8 times 2 is 16.
Yeah, okay, so 2 16ths. So then that's all the way here. So, okay, maybe we just start with this. Oops. It's going to be something like that. It's going to be pretty steep, pretty quick. Okay. All right, so that would be y equals x to the fourth. Right? Y equals 1?
you draw a line.
Yeah, at y equals 1. Okay, so it looks like we're trying to find this area then. Because that's the area bound between those two curves.
Yeah.
Okay, good so far?
Mm-hmm.
All right, how are we going to do this? Well, I need to find the area of the top function first. So which one would be the top function?
Y equals x to the 4th. Oh, wait, no, it'd be y to the equals 1, actually.
Yeah, so this is going to be my top function because it is higher than the other one in terms of the area there. Okay, so that'll be the first one. So I need to find the integral. I'll keep the green. Integral
From
of 1 dx from what to what though?
negative 1 to 1.
How do you know?
Because it's bound by x to the 4th.
It's where the y graph, or sorry, what do we call it, the blue one? I call it G-index. Yeah, it's where y equals 1 intersects y equals x to the fourth. And so that
And you just pull a straight line down.
Yeah, so they intersect at those points, right? Super easy in this case for us to see that. Sometimes it's a little more difficult to find those intersection points, but that's a key part of this process. I draw the graph, I can see the area that we're trying to calculate, and then I need to go, oh, okay, I need to find out where it is that they intersect. In this case, it's really obvious that they intersect at negative 1 and 1.
Mm-hmm.
Okay, so then I know that I'm taking the integral from negative 1 to 1 of 1 dx. Okay, so what's that?
2.
2?
Square units.
Okay, and you did that how?
Well, I did just mentally, which isn't proper, but
Right?
it would just be 1 would turn into just, yeah. do derivative.
Okay. All right, so we have the area of the top one, and now we need to subtract the area of the bottom one, because that would be this area right here. We need to subtract this stuff away. So let's take the same integral and subtract that away. So the integral from -1 to 1 of x to the 4th dx.
Which should just be.
X to the 5th over 5.
Excuse me. Oh, yep.
Yep.
1/5 minus -1/5.
2/5.
Okay, and then I need to subtract those values. So 2 minus 2/5.
Should be.
8/5.
See.
There you go. So the area between these two curves is equal to 8/5. Okay, what questions do you have? This is a super easy example, but that's pretty much how they all work. Graph it, find the top function, take its integral, find the bottom function, take its integral, subtract it.
What's a equation that you can do to find those intersection points? Is there an equation?
That's a good question. There's not really an equation, but
Wouldn't it be x?
either you could just think about it, or if you want to find where they intersect,
What's where their x values are the same?
it's where their x values are the same.
And
So what I would do is I would set x to the 4th
no, it's where their x
equal
and
to
y
1.
values are the same.
Yes. Yes.
Oh yeah.
So that's why I could just set then x to the 4th equals 1, and then solve for x, and it would tell me the x values. Does that make sense?
Oh yeah, because that makes sense. Because like, 1 is equal to 1 to the 4th, and 1 is equal to 1.
And so if I want to find where these intersect,
Yeah.
I would just go 5x minus 2 equals 2x plus 3, and that will tell me the x value where they are the same. And then that way I'd be able to just know, okay, that's the exact x value where they intersect.
Yeah.
And that'll work with all these functions, where you just set them equal to each other and then solve to find the intersection values, which might be 2, it might be 3, typically it's 2. Okay? We'll talk about if it's 3 another time. Okay, let's keep going. Let's see this one. Find the area between y equals x squared and y equals x to the 3rd. Let's make a graph. Try to visualize these in your head to get started. Where are these going to intersect? What do these graphs look like? So where is that area going to be bounded? So before we start our picture, you know, where should we focus it in?
1. And
What does x squared look like?
just parabola.
What does x to the 3rd look like? Right, for you guys, I think it goes this way, right? So you've got x squared, and then you have x to the 3rd. So where's the area going to be bounded between them?
It's gonna be like on the right hand side of the y-axis. It's probably gonna be at 1. It's gonna be at 1, yeah, for sure.
Yeah, they could intersect at 1.
1 is equal to 1 squared, and 1 is equal to 1 cubed.
Right. Yep. Okay. Right. Is it going to be the area is bounded between them when x is greater than 1 or when x is less than 1?
I believe less.
Great.
No, because like if you think about it, it's gonna look like this, and then this is gonna be like this, and then this would cross somewhere at 1, And this is gonna continue going up, and it'd be like this small area right here.
Wait, isn't x to the third this way?
No, it's because like the negative values are really negative and positive values are really positive. Because you're cubing it. Squared, it's like the parabola. Because like you basically are just like,
Oh,
because like, yeah.
sorry. I had x to the third reference. Yes.
Wait, this one's gonna look something like this. This is gonna come up.
So I've got y equals x squared in here. And we know that y equals x to the third is also going to intersect here and here, right?
Mm-hmm.
At 1, 1, and 0, 0. Okay, so I mean, it's going to intersect at x is less than 1, but does the graph look like this? Or does the graph look like this?
Oh, wait, that's actually a good point because if you think of like 0.5 cubed is going to be more than 0.5 squared.
Mm.
So I think it's going to
Yeah,
be...
so like 0.5.
The x cubed is going to be underneath it. It's going to shoot up quick.
You think which one is underneath?
X cubed. And it's going to shoot up through x squared.
So you would propose this?
I would guess that, yes.
Okay. Can we know for sure?
Yes. We can test.
How?
Test like 0.8.
Oh yeah, let's test some
And then
values.
1.1.
Yeah, grab a calculator, throw in like
I'll
0.5
just
times
test
0.5
0.9
times
and-
0.5 and see what happens.
I'll just do 0.9 and 1.1. Right? That makes sense? Like,
Sure, you can do whatever points you want. We just need to see, because we know either it's going to be entirely above or entirely below during that interval from 0 to 1, right?
So
So you can pick 0.9 and then
1.1
plug them into
cubed
both.
is 1.3.
1.9 cubed,
Is 1.3.
okay. 1.9,
So 1.1.
I don't want 1.1. That's outside of our,
1.9 square.
something between 0 and 1. We need to know, is in between 0 and 1, is x to the third above x squared or is x to the third below x squared? In between 0 and 1.
So for 0.9, 0.9 squared is 0.81 and 0.9 cubed is 0.72. So it's less.
Which one's less?
X cubed
Okay,
at 0.9.
so it's below at 0.9.
Yeah.
Okay. Is it reasonable to say that it will be below all the way through 0 to 1?
Yes.
Yes.
Yeah. Okay, so we know it's going to be something like this. And then it's going to be bigger above 1. And then it's going to come back down this way. But we don't really need that part of it because there's no area bound between the curves over there. So it looks like we're trying to find this area here.
Mm-hmm. So
Pretty small.
it's the
From 0 to 1.
From 0 to 1. So the integral from 0 to 1 of, which one's the top one?
x squared.
X squared dx. Here we could do, I'll do it this way. Dx minus the integral from 0 to 1. Which one's the bottom one?
X cubed.
X cubed. Properties of integrals. Think of your properties of integrals.
Oh.
I could combine these into one integral, could I not?
Mm-hmm.
I could, because they have the same bounds, I could do 0 to 1 of x squared minus x to the third dx. And now I only have to do it one time instead of two different integrals. Okay?
Smart.
And then that turns into x cubed over 3 minus x quadruple. What's that called?
To the fourth power.
X to the fourth.
You need to have a word for that.
We don't have a word for it, unfortunately.
Quads.
Timed. I'm gonna say timed because it's
Time, because fourth dimension.
step up, down, left, right.
We don't have a word for it because this is the fourth dimension, so
Timed.
which is time. So
X to the time power over 4.
x to the time.
Wait, what comes
divided by
after
4.
time?
And the fifth dimension, we don't know what it is.
Is that actually what that represents? The fourth dimension?
Yeah,
Basically.
I mean, like if you think of like a line, that would be a one-dimensional thing. Has only length. Two-dimensional would be like an x squared. You know, think of a little square area. That'd be 2 dimensions. Volume would be 3 dimensions, so you would have x to the third. And then what's the fourth dimension? Oh, well, that's time, because 3D objects
So is
move
it
through
like
time.
the
So then,
soul? Is
What's
it
up?
like your soul or something?
That was
Maybe.
plasma. No, I'm thinking.
Plasma's
I'm
a
thinking materials.
like a substance.
yeah, those would be phases of matter.
Yeah.
Anyways, let's finish this. Oh, this is easy. There's a 0 in here. Haha. 1/3 minus 1/4, right?
Yeah.
Minus 0.
Equals 3/12.
No.
It's
I
not
got
3/12. Sorry, 1/12. Sorry, yeah. 4/12
Yeah.
minus 3/12.
We know it's twelfths.
It's okay, arithmetic is hard. Calculus is easy. Okay. There you go. The area between these is 1/12. How fun. Okay.
What?
Okay.
Wait, so if you have x to the 5th, that area would be bigger or smaller?
Bigger.
Good question.
Wait.
Wait, we can actually test it.
Why don't we just find out?
Consult the calculator.
It would be bigger because 1.9 to the 5th is only half a point.
Pretty much the only thing that would change here is that would be a 6 and that would be a 6.
So it'd be
So you'd be subtracting
1/12 minus
a
1/6.
6 instead of subtracting a 4.
So it'd be 2/12. It'd be double the size. What?
Fascinating.
I think that's kind of weird.
Wait a minute.
So it would be a bigger area.
Yeah.
Because you'd be kind of
How's that 2 twelfths?
you'd be kind of pulling this blue one down further. You'd be like stretching
Yeah.
it if you had it to the 5th power. This would be x to the 3rd over 3. This would be x to the 6th over 6. So then you plug in 1, you would get 1/3 minus the 6th.
Which would be 1/12.
2/12.
Isn't it 2?
Because a third is
1/3.
4/12. And a 6th is 2/12. So 4/12 minus 2/12 is 2/12.
Mm-hmm.
Right.
There you go. Very cool. Okay, not too bad. All right, we could kind of review the general steps if you want to. How would we summarize the steps that we need to do? Like, what kind of information do we need to like generally do this?
We need the equations for both graphs.
Yeah, okay, yeah, you need the equations for both graphs.
We need bounds.
Yep, so I would say that's the first thing is find the intersections. You'll always, almost always be given the functions. Sometimes you have to go find the function. Like maybe I ask you to like find the tangent line or something and that becomes your other function or something. But I would say the first thing is find the intersections. And if you're in my class, I'll require that you graph them, but you probably won't have to graph them on the test. Okay, you found the intersections. Now what are you going to do?
I'm gonna find the integral for both. For the
Set
top
up
one,
integrals for both.
calculate the integrals for both of them.
Yep. Calculate the integrals.
And then we're gonna take the topmost one and subtract it from the bottom one. Can Can I say greatest interval? Would that be accurate?
That will be accurate, yeah, most of the time.
Are these measured in net area or total area?
That's a great question. So that's what we need to talk about next.
I think it's
So with the area under the curve, we're always going to assume the absolute value. So we're not going to do signed area.
yeah, because you can have negative area between two curves.
Right.
You could have 0, and then they'd just be the same thing.
Yeah, so I mean, if you had a situation like and let me see if I can come up with something.
X to the
off
cubed and
the-
x to the
off the top
fifth.
of my head.
Oh wait.
X cubed, x to the fifth.
No, that'd still be positive.
No, that could work. I'll do a really bad x to the third and then a really bad x to the fifth. It would be,
Yeah.
right? So then you could find like, okay, I want to know between this point and this point, I want to find that area. If you did signed area, because those are odd functions, then we wash out, it would be 0.
Mhm.
We're going to always assume the absolute value. We're going to take the total area and not the signed area for the area between two curves. Okay?
Makes
What
sense.
if you wanted to find the area underneath the x-axis between two curves?
If you did want to find like the actual signed area between two curves, you could. You just have to be then really careful about which part is negative and which part is positive, and then correctly combine them. It's possible, totally reasonable to do. It's actually not even hard. You just have to keep track of which part you've calculated as negative and which part. So you'd probably have to have multiple integrals that are negative and positive portions that then you could keep track of to know, oh, I need to subtract this part away and add this part depending on the function. Okay? Great. All right, let's do this one. Calculate the area bounded by the curves x equals y squared minus 4, y equals 2 minus x. I mean, okay, what does this look like?
Ooh. Oh wait, no, it's the y's are on the same side. I think that's weird.
Wait, what's weird?
You should just rewrite it.
I should rewrite it.
I'm just gonna rewrite it.
Well, I've given you f of y essentially here, right?
Yeah. But only on one side.
Yeah, so it's kind of weird, isn't it?
Just rewrite it to f of x.
Well, what does that graph look like? Y squared minus 4.
It'd be the square root of x minus plus 4.
What does it look
It'd
like?
be a parabola and then shifted down 4.
No, it wouldn't be a parabola. Because it's the square root.
Because to get the squared off the y, you're gonna have to square root the x. Yeah, what does the square root? Oh! No, it's not even an inverse parabola. What does that look like? What is y to the square root of x equals square root of x?
Yeah, it's a parabola.
Your calculator's not going to help you. Because this is the x-axis and this is the y-axis.
Yeah, so you have to switch it around first. So then you have, just switch it to y equals the square root of x plus 4. Y equals 2 minus x. Those are your two
If
equations.
you do that, you're going to have the plus minus,
Oh, that would help us all.
right? Can't forget plus minus on square roots.
Can you put them both into x equals graphs?
Is that easier?
Yeah, I could rearrange this to say x equals, right? X equals
-2.
2 minus y. Right?
Yeah.
Okay. Now they're both in x equals. Can I graph them now?
I mean, yeah. It's weird.
It's weird. Let's just plug in some points.
So
You probably haven't had much exposure to doing functions not in terms of x, but this is completely valid to do.
So 1 would equal. Oh,
Negative,
1's not a good one.
-3.
Well, so like if you plug in 1 for y, what's the x value?
-3.
Okay, so you get 1, 2, 3, 1.
Oh, it's the same for both. That's our point that they meet at.
Okay.
If you plug in -1, wait,
I'm not gonna get, if I plug in 1 for y, I'm not gonna get -3 here, Michael. Okay, if you plug in 0 for for y,
you get -4.
-4.
2.
Okay. I'm gonna change the colors. This one. Okay, tell me more points.
If you plug in 3,
You get 5.
you get 5.
Y equals 3.
Y equals 3.
Why did we skip 2?
That's a good question. We're gonna get 0 for 2.
Okay, so we'll have 0 for 2.
Mm-hmm.
Okay.
Wait, how do we get 0? Oh, yeah.
And then for your x, or for your second, do we do the second equation?
No, we don't necessarily have an accurate picture of this one yet.
Okay, we did 1.
Because we've only plugged in positive y values.
3. If you do -1,
What happens if you put in -1?
it just be -3.
Yeah.
-3.
-2 would be also 0.
Okay.
Hold up, it doesn't even. It's
What?
Just
It
be the
doesn't
same.
pass the vertical line test now.
It's the same thing because it's just the square.
This isn't a function.
Indeed, it is not a function because it is in terms of y instead of x. It's okay.
Serious?
We just have to find the area between these curves. Doesn't matter if they're functions.
It doesn't have to pass the vertical line test?
We're dealing with imaginary functions now.
What?
We've moved
This
out
is
of
not
the-
an imaginary function. It's just-
Oh, because it's plus
Not
or
a
minus,
function.
duh. So it's going to look like a parabola rotated by 90 degrees.
Yeah, this is just going to open right. This is a parabola that opens right since it's in terms of y instead of in terms of x. This is your curve.
Oh.
This is the curve x equals y squared minus 4.
Yeah.
Great. Now let's graph the curve x equals 2 minus y.
If you plug in 0, it's going to be 2.
Plug in 0 for y, it's going to be 2 on x.
Mhm.
Alright,
If you plug in 1 for y, it's going to be 1.
okay, right here.
If you plug in 2 for y, it's going to be 0 again.
Okay,
If you plug in 3, it's going to be -1.
plug in 3 for y.
This is just a horizontal
Two.
line.
Yeah. This
It's
is-
certainly not horizontal.
Sorry, it's just a linear line.
It's a linear equation because everything is in terms of 1 degree. Now, it's not going to be perfect because it's a human scale, so we'll pretend. Alright, so there you go. We've graphed the curves.
It's so weird.
So the area between these curves we want to calculate.
It looks like it intersects on y equals 2.
They intersect at y equals 2,
Or x equals 0.
so y equals 2 is an intersect point.
Also looks like they intersect on y equals -2. But for x it was 5. What?
Now, again, this is a human scale, so it's going to be really hard to see this with the graphs. So this is where now we should try, let's set them equal to each other and just solve. So it's a good thing we've already put this in terms of x, because now I could just put them as
2 minus
y squared minus 4
equals 2 minus y.
equals 2 minus y. Okay, and that'll tell us where they intersect. Solve for y.
Y equals plus or minus the square root of 6 minus y.
Now you have a y on both sides.
No. You get out of y. Y plus y equals 6. Or set it equals 0.
You can reverse one.
Yeah, that's called a factor.
And we know one is 2.
Y plus 2, or y plus 3, and then y minus 2.
Yeah.
Oops. So then what are the values of y?
2 and -3.
So they're going to intersect at y is -3 and y is 2. Right?
Yeah.
Okay. So we know they intersect at those points, so there you go. It's at -3 apparently.
That's what they say.
Okay. You could check that by plugging in -3 to both, and you'd see they get the same value. But okay, we've done really honestly the hard part now. But this is the area that we're trying to calculate here.
So how do you set that up?
So here's the interesting thing about this one. This is why this is such an important example to do. But notice that we've done everything in terms of y, because if I tried to solve this for x, I'm going to get those two weird functions, and then how my gets weird. So we can actually integrate with respect to y instead. It doesn't matter which variable we use. Integration rules will work the same way. But I can integrate with respect to y, and so I would find the integral from y equals something to y equals something.
Of of something
Of, right, f of y minus g of y, whatever the functions are, dy. All I have to do, I'm just changing all of the x's that I would normally see into y's, so it'll work the same way. Does that make sense? So let's think through, let's fill it in. I would have
So it's
the integral from y equals
-3
-3
to 2.
to y equals 2. And then now we have to think, okay, so what's going to be the top function? Now this is tricky because when we were doing it with in terms of x, the top function was whichever one was like highest on the y-axis essentially. So we were looking from the top minus the bottom because we were with respect to x.
Yeah.
But if we want to integrate with respect to y, it's like we've rotated it. Let me see. Maybe for you guys, we've rotated it 90 degrees. So we've taken it from looking at top to bottom, and now we need to ask right to left.
So blue is our biggest one actually.
So blue is our top function, which is 2 minus y,
Yeah.
minus our bottom function, which is our left one, which is y squared minus 4. Let me rewrite it with more room. Notice the parentheses are really important here actually because we're subtracting the whole function. Y squared minus 4.
Yeah.
So I can't just write minus y squared because then I don't only subtract the y squared. But I'm subtracting this whole function away. So I would have to distribute the negative or otherwise it
So
counts.
that's 2y minus y squared over 2. Though it would be that it'd be
Negative y squared over 2.
yeah.
Negative y squared what?
Over
No, it'd be 2y minus y squared over 2.
What?
Because the 2.
2 minus y squared plus 4, right?
No.
Yes, because negative times negative is positive.
I just have to distribute
Oh,
this
sorry, you're
negative.
making it one function. Yeah. I thought you were on the antiderivative first.
Oh, I see. No, I just started right away throwing them in the same one. You could do two different integrals. If you want to do it that way, that's totally fine. Might as well save some time. Make them one.
So then it's 2y minus y squared over 2.
2 no. Oh,
We're
you're
doing
taking
it
it.
there.
You're okay. Sure, we can do that.
Can you just combine them? So then it'd be 6.
Yeah, I mean, you could combine like terms first.
6 minus
Oh, yeah.
y cubed.
You could take the antiderivative now, or combine like terms, and it's going to get you the same answer either way.
Mm-hmm.
Okay.
Can you combine the y's?
No.
Oh, they're different.
They are not like terms.
So now it's 6y minus y squared over 2 minus y cubed over 3.
Which return to
So
0
that'd be
minus
12
1
minus 2
minus y squared over 2
minus
y cubed 2 over 3.
A lot of arithmetic. Use a calculator. Actually, you could probably do this mostly in your head. 12 minus 2 minus 8/3. Minus negative 18 minus 9/2 minus plus 9.
I have 38.33 repeating.
Mm-mm.
12 minus 2 minus 8 thirds plus 18 plus 9/2 plus
Minus 9.
minus 18. Oh, I have plus. Yeah, so it's plus 18 minus 9. Oh, I have.
I can check my work.
Okay, no, you're right. Yeah, it's 20.83.
Yeah, there you go.
20 and a third.
And
That's the multiplier.
do math enter.
20 and 1/3.
What's math enter give us?
One change.
Mathematicians prefer improper fractions because it has all the information you need.
Number. .e to the negative. 125 over 6.
Yeah. You good over there, Jonah?
Hmm?
You good over there?
Or 20.8.
3 repeated. Okay.
Sauce.
Boom sauce. There you go. Okay, here's a couple. There's one in terms of y, there's one in terms of x. Your turn. Have fun.
I'm trying to think, why can't example 5 be in terms of y?
Could be.
Y
But
is negative
there's a typo. That should be squared.
Oh, okay. Now it can't be.
Now it can. Which way is this going to open?
To the right? To the left.
To the left. This negative, so like when we have a positive y squared, it opened right. Since it's negative y squared, it's going to open left. What? Oh, that's crazy.
Yeah, that clock is slow.
That's super wrong. Well, that's okay. We'll just pick it up on Wednesday.
Wait.
We got as far as we needed to, so.
Look, Josh.